Okay, so hey everyone, my name is Christian, and this is my first part of my air quality control system project. It's just some background and information. So, ambient air pollution has been causing an extreme number of deaths over the last few decades with all of the emergence of the developing countries and all of their power generation and all the cars and trucks that are now on the road. And so it was estimated in 2016 that about 4.2 million people died just due to particulate matter for air pollution. So most of these come from a few common diseases from this exposure, and they include lung cancer, cardiovascular disease, asthma, and chronic obstructive pulmonary disease. And in terms of almost all instances, treating ambient pollution from its source is the best way to go about it. But in these major cities, uh, it doesn't seem like enough progress is being made for this to make it so that people aren't getting hurt. And so having something to control this ambient air pollution might be a good route. And there are currently two pollution control towers that are located in China. You can see them on the right. So the bottom figure is an electrostatic precipitator that's in Beijing, and it just uses its technology to um, energize the particles and bring it down and then collect it. And then the one on the top is much taller. It's about 100 meters in height. And it uses kind of this greenhouse effect where, if you can see on the bottom, it's a glass encasing. And so the pollution comes in, and then it uses natural convection because the air heats up and then goes through this tower and goes through a bunch of different filters and layers and stuff like that, and then comes out. And that one is supposed to be able to clean 10 kilometers squared of air, which is really, really, really good. So, uh, some of the figures on capital investment due to ambient air pollution, it was estimated that yearly India spends about $80 billion on this, and China spends $38 billion on just people getting sick due to this air pollution. So it's definitely a worthwhile investment. And then the World Health Organization guidelines. I just wanted to make a chart of these. Your PM 2.5 levels, annual mean and 24-hour mean are 10 micrograms per meter cubed and 25 respectively. And then your PM 10 levels are exactly double that. So these are two tables that I thought were important to share, and they show the differences in PM 2.5 concentrations and PM 10 concentrations in between China, India, and the US. And in China, if you look at these tables, you can see that the maximum values of PM 2.5 and PM 10 are over 12 times the recommended World Health Organization standards. And basically, the numbers that you see for India are even worse. So there's a very big discrepancy between even the mean values and what is recommended by the World Health Organization. But if you look at the United States, you can see that none of the levels are above the what is recommended on an annual basis. So for the system definition, the major sources of pollution in countries such as China or India are manufacturing plants, gasoline and diesel emissions from cars and trucks, coal-fired power plants for electricity generation, and then the chemicals that are emitted due to these sources are cars emit a lot of VOCs, carbon monoxide, and sulfur dioxide, and of course particulates. And then manufacturing coal-fired powered plants emit soot, which is mostly black carbon, smog, which is nitrous oxides, sulfate, and the particulate matter. And so the whole point of this device is try to be able to put it in urban settings in order to cleanse a certain area. So you're not cleansing the entire city, but you're trying to cleanse, a certain area such as a market, um, some section of a university, a major transportation hub, or bus stops or something such as that. Maybe popular crossing areas that have a lot of car traffic, and then or just something like a community park. And so the effects of particulate matter on human beings. Um, in most cases, the larger that the particle that you have, the less effect that it has on humans. Larger particles tend to settle to the ground in a much shorter period of time, and oftentimes can't get into a human's respiratory system because it's too big. Because small particles do not settle, they're a lot more difficult to control using these technologies, and are also airborne for longer periods of time. And some of the environmental impacts of particulate matter include acid rain, damaging forests and farmland, and decreasing the nutrient levels in soils. So, some external properties that have to get taken into consideration for this project: weather. So, you have humidity and rain that are going to be affecting the base of this material. And so, stainless steel is going to be recommended as the choice because it's very good, and it's very anti-corrosive, opposed to mild steel that might rust and would give you a much shorter life for the unit. And then a protective hood must be used in order to keep water from entering the control technology device. And that's basically located on the top, right above where the fan is going to be. And it's just to make it so that the filters don't get wet and the particulates that are captured in the hopper aren't getting wet also. And then finally, the system boundary is just you have the device, and then the total amount of area that the device is able to cleanse the air is that box that's around it. So for the major system component selection, first off, we have basically I went through and tried to compare all of the different air quality control technology devices that we have learned in this class. So your spray tower scrubbers is going to usually not be very efficient for small particle sizes, and it also you have to dispose of liquid particulate, which is also something that is not desirable because it costs a lot more money. It's harder to do. So that was X'd out. You have your cyclones, which are also pretty bad with particles and not very efficient with particles that are within the PM 2.5 range. And a lot of the PM 2.5 is what's affecting humans so much with ambient air pollution. So that was also eliminated. And then you have your electrostatic precipitators, which have high upfront costs but require relatively low capital costs for operating. And the efficiencies for small particles are really good. And then you have your filter bag houses, and they have really high efficiencies for small particles, but have to be serviced frequently and have high maintenance costs. So I just created this table in order to try to show just the comparison between the two. Just the upfront cost of the base unit for the ESP is almost 2.5 times greater. The filter baghouse gave a higher allowable CFM, and the efficiency of the filter baghouse is most likely going to be above that 99% mark. And then also with the ESP, it requires high voltages in order to energize the particles. And having this high voltage machinery in public areas can be potentially very dangerous. So for your shaker versus your reverse filter baghouse, these are just the two main designs. The reason why reverse air filter baghouse wasn't chosen in this particular equipment was because you have to, in order for you to cleanse the air in a reverse air filter backhouse, you need to use one of the components. And in order to do this, and so one of the components basically won't be running and sucking in air and cleansing air. And so in this particular case, we only have 4 components that are being used, and so 25% of the total airflow will not be running through the units at any given time. The only downfall of the shaker unit is that the fans actually have to be ramped down once the shaker device is in use, which takes about 2 minutes. But your runtime is usually 45 minutes for the fans being on. So you have 45 minutes of the fans being on, and then you have to ramp them down. The shaker device does its thing for 2 minutes, and then you can ramp the fans back up for another 45 minutes. So this is a process flow design that I created. You have your airflow coming in, going into the filter baghouse. The particles are collected. It goes through an air intake louver, collected on the filters, and then the fan will be ramped down, and the particles can go down into the hopper, and then the fan will ramp back up. The power is coming from a combination of solar panels and regular power generation that might come from, the coal-fired power plant or whatever power generation, how the city gets its power. Your exiting airflow is at 99% less particles, and then you have your protective hood on top. For the mass balance, kind of the same idea. You have your internal mass flow rate from the concentration as well as the total allowable CFM. Your M dot out is going to be 99 or at 1% of your M dot in, and that leaves your mass accumulation inside the unit that's intercepted by the filters and gathered in the hopper as 0.026928 grams per minute. So for the major component design specifications, there are a few assumptions that had to be taken into account. First, the unit has to fit within a 10 foot by 10 foot by 10 foot volume. Also, the assumption was made that the PM10 data that was shown above actually also includes all of the data for that would be under PM2.5 as well, because the PM10 is basically all of the particles below 10 microns. Finally, the pressure drop caused by the structure was assumed to be negligible. So for the filter specifications, they just kind of come from the total dimensions. You have a 5-inch diameter, and they're 8 feet in length each. And then just some of the numbers that I came up with is you would have 196 total filter bags. The filtration area would be about 10 feet squared per bag. And your net cloth area is about 2,000 feet squared for an allowable CFM of 12,000. And according to the textbook, this 12,000 CFM corresponds to 4 compartments. And so you would have 49 bags per compartment. For this filter bag material, usually you have to take into account the temperature, cost, and whether or not it can handle the chemical makeup. Since it's ambient air, most materials are going to be able to do well with the thermal properties because, it's just ambient temperature. And so in this case, polyethylene was chosen just because of its high durability and its low cost. For the pressure drop calculation, it was basically found that the pressure drop due to the filters was 2.5 inches of water, and the area of cleansed air came out to be about 0.124 kilometers squared, which is actually equal to the area of 23 football fields, but this is with a very large assumption that the air volume height does not exceed 10 feet. So in terms of ancillary equipment, fan specifications, you have 4 fans total, 1 per compartment, with about 3,000 CFM each, and the pressure drop of 2.5 inches of water. And so using some interpolation, you just find that it's around 1,200 RPM, and the brake horsepower value is 1.71 for power, running at 24/7. Those are the numbers for the kilowatt hour that you would need per year. And then I ran the numbers for the solar panel usage. You would need 30 meters squared for all the power generation. And on the outside of the unit, not including the air intake louver, you would have about 22.3 meters squared available. And so about 30% of the electricity would not be accounted for. In terms of cost analysis, I'm not going to read everything. Basically, the total install cost would be about $202,000, not including the fan, solar panels, and protective hood. And including those, it's an extra $54,000. And then for your cost analysis, for your annual maintenance, the power with your solar panel usage is about $1,200 annually. And then your filter bag replacement, usually you replace the filters biannually, so you cut the entire price of the filters in half, and you get about $625. And then your bi-weekly maintenance is $1,500, and that was found just by using that a technician would look at these once every 2 weeks at 2 hours for about $20 per hour in payment, and then your total is around $3,400 per year. And then for project management, obviously one of the most important tools that you need is a budget. Once you have your budget, you can go to your design team, and once you have that final design, you can start doing all your scheduling, all your final budgeting, and making sure that everything, all the resources are allocated and all of them are accounted for. Permitting, since it's relatively new devices, this permitting step might be pretty involved and require a substantial amount of resources. And finding a place to dispose of the particulate matter will be one of the biggest sections related to this. Some of the risks involved could include safety and the possibility of damaging the equipment due to natural disasters or urban accidents. And finally, for a new project like this, compliance is mostly based upon the expectations that are set from the design specifications. And so monitoring to ensure that the unit is performing at that level that it was designed for must be considered to justify the cost. So here are my references. Thank you very much for watching, and I hope you enjoyed it.